Welcome to This Explainer. Today, we're diving into the complex probabilistic reasoning that actually powers machine learning decisions. Whether it's your email filtering out spam, your bank flagging a weird credit card purchase, or an algorithm deciding who gets a job interview, this math is silently shaping your daily life. If you've ever wondered exactly how artificial intelligence processes our messy, unpredictable world, well, you're in the right place.
Let's kick things off with a classic, counterintuitive puzzle from Problem Set 4 to test your human intuition against statistical reality. Imagine this. A medical test is 95% accurate. You take the test, and unfortunately, the result comes back positive. What is the probability that you actually have the disease? Take a second to really think about it. Most people immediately shout, well, 95%, obviously. Keep your answer locked in, because the mathematical truth we uncover a bit later might completely shock you.
Here's our roadmap for today. We've got 6 key steps: navigating AI's uncertainty, unpacking the core probability toolkit, seeing Bayes' rule in action, exploring conditional independence, breaking down naive Bayes classification, and finally, looking at its power and limitations. Let's jump right in.
Section 1. Navigating AI's uncertainty. To understand how AI makes decisions, we first have to give it a toolkit for handling uncertainty using probability theory.
Let's lay down some quick ground rules. First up is marginal probability. This simply looks at one isolated event occurring, like the probability of flipping a coin and getting heads, totally on its own. But we all know the real world is complicated, so we also need joint probability. This looks at multiple events happening at the exact same time. For example, calculating the probability of a person being both female and tuning into a highly specific reality TV show on a Tuesday night. It's two distinct factors intersecting.
We can see this perfectly with a practical example straight from Problem Set 4. Imagine we have data on 100 customers buying t-shirts. Look at the outer edges or the margins of our data. The overall probability of a customer wanting a small size, regardless of the color, is a marginal probability. In this case, it's 30 out of 100, or 30%. But if you dive into the inner cells, you get the joint probabilities. What's the chance of someone wanting a shirt that is both red and large? We just find where red and large intersect, and that gives us 30 out of our 100 total customers. So our joint probability is 30%.
And that brings us to conditional probability. This right here is where things get really interesting for machine learning. Conditional probability calculates how likely event A is, given that we already know event B has occurred. We calculate this by taking the joint probability of A and B happening together and dividing it by the probability of B alone. Event B acts as our normalizing constant. Ultimately, it's all about dynamically updating our knowledge based on new, incoming information.
Section 2. Bayes' rule in action. Let's see how this actually builds our ability to update our beliefs when new evidence rolls in.
Okay, so back to that opening question from the problem set. Remember the medical test with 95% accuracy? Well, even with a positive result, your true chance of actually having the disease is a shocking 15.6%. Crazy, right? How did we get there mathematically? According to Bayes' rule, we take the true positive rate, which is 95%, and multiply it by the baseline chance of having the disease. Then we divide that number by the total probability of anyone testing positive at all, whether they are actually sick or just a false alarm.
So how does that happen? The secret sauce here is something called the prior probability. In our source example, the baseline prevalence of this disease in the population is incredibly low, just 0.8%. That means 99.2% of the population is perfectly healthy. Because there is such a massive pool of healthy people, that tiny 5% error rate of the test produces an enormous number of false positives. The false alarms completely drown out the actual sick people. This is the perfect proof of why our human intuition desperately needs rigorous mathematical frameworks to avoid jumping to the completely wrong conclusions.
Section 3. The conditional independence assumption. Before we can build a functional AI, we need to understand a massive mathematical shortcut.
Think of it like this. A patient walks in with a cough and a fever. Normally, these two symptoms are highly correlated. However, if a doctor already definitively knows the patient has the flu, let's call that event C, then knowing they also have a cough tells the doctor absolutely nothing new about whether they have a fever. The relationship between the cough and the fever is entirely explained away by the presence of the flu. Making this assumption makes calculating complex, multivariable probabilities vastly simpler.
Section 4. Naive Bayes classification. Let's take all of this and apply it directly to machine learning. Think of this AI model as a detective working through 4 distinct steps. First, it prepares labeled data. Second, it estimates prior and likelihood probabilities. Third, it applies Bayes' rule.
And fourth, it predicts the class with the highest posterior probability. But to do all of this at scale and quickly, it makes one massive, naive assumption. It pretends that all of its clues, every single feature it looks at, are completely conditionally independent of one another. Ignoring how features actually interact in the real world is definitely a naive simplification, but it is exactly what makes the math manageable for computers.
To put this in perspective, imagine we're training our model on a dataset of 100 emails to estimate the likelihood of words like free, win, and money appearing in spam versus normal messages. Instead of trying to calculate the astronomically complex probability of all three words appearing together in a specific sequence, the naive Bayes classifier takes the easy route. It just calculates the probability of each word individually. So 30 over 50 for the word free appearing in spam, 25 over 50 for win, 20 over 50 for money. It then simply multiplies those individual fractions together. It essentially assumes the word free has absolutely no relationship to the word money, which is definitely naive, but computationally, it's brilliant.
Section 5. AI in the real world. Detecting bias. Let's pressure test this logic against a real-world scenario from Problem 20.
Imagine an AI resume screening tool. Let's first look at the shared traits of successful candidates. According to the historical data in the problem, 90% of successfully hired candidates have great coding experience, and 85% come from top universities. Let's say our candidate has both. Excellent. But now, let's introduce the historical hiring baseline. Historically, only 20% of the hired candidates at this company were minorities, while 80% were non-minorities. We need to calculate the posterior probability of our highly qualified candidate being hired based on whether they are a minority or non-minority.
And here is exactly where the math shows us how algorithms can perpetuate historical bias. Let's multiply the probabilities step by step. For both candidates, we multiply the 0.9 coding score, the 0.85 university score, and the 0.7 base hiring rate. Everything is identical so far. But watch the final step. Because historical training data heavily favored non-minorities, we must multiply the minority candidate score by a prior probability of just 0.2, while the non-minority candidate score is multiplied by 0.8. The math blindly penalizes the minority candidate. The model isn't actively thinking. It is just multiplying fractions, which mathematically drags down an equally qualified candidate based strictly on past data.
Section 6. Power and Limitations. As we wrap things up, we need to balance what this model does beautifully against where it falls short.
While naive Bayes is incredibly efficient and honestly fantastic for text classification like spam filters, its strict assumption of independence makes it pretty clumsy when features are actually deeply correlated in reality. But perhaps its most fascinating flaw is the zero-frequency problem. Remember, the entire algorithm relies on multiplying probabilities together. Basic arithmetic tells us that anything multiplied by zero is zero. So if the AI encounters a feature it has literally never seen before in its training data, meaning it calculates a probability of zero, the entire equation collapses to zero, completely paralyzing the AI's ability to make a prediction.
So, I'm going to leave you with this thought to ponder. If a single zero ruins the whole equation, how must we adjust our math to handle the unexpected? The real world throws curveballs every single day, and an AI that breaks the second it sees something brand new isn't very intelligent at all. Thanks so much for joining me on this explainer, and keep questioning the math behind the machine.